Hello everyone, welcome to my talk titled Understanding Robots, Making Robotic Movements Clear in Multi-Party Interactions. My name is Miguel Faria, and this work was done in collaboration with Professors Melo and Paiva from Legible. This work will have the following outline. I'll start by presenting the motivation behind this work, then I'll talk about our multi-party legibility framework, then I'll present the user study we conducted that validated said framework, and I'll end this presentation with some final remarks regarding the work overall. So the motivation for this work stems from the fact that nowadays we can find robots outside of factory settings interacting with humans in the most varied applications. Some of them are collaborating with humans in therapeutic tasks, helping the elderly develop their cognitive skills to lead more fulfilled and healthy lives, or even assist humans in shopping malls, guiding them towards their intended stores. Across all of these different applications, the key aspect is the correct communication of the intentions by the robot to the humans he's interacting with. So, to improve a robot's expressiveness, legible movements were designed to shape a robot's movements so that while he moves closer to his intended goal, he moves as far away as possible from other possible goals, and as soon as possible, so humans have more time to adapt to his movements. These types of movements have been shown to improve a robot's efficiency in human-robot collaboration tasks, both in the single-user and in the multi-party interaction case. However, in multi-party interactions, we have multiple users interacting with the same robot, and this leads to multiple perspectives over the same movement that need to be combined into a single metric. So, we are interested in understanding if, in interactions with multiple users simultaneously, does combining their perceived views of a robot's movement improve the movement's legibility? And why are these perspectives so important? By having multiple perspectives over the same movement, we can end up with having different users having different understandings of the robot's intentions. Let's take the example before you. Here we have two humans, Mary and John, expecting the robot to fill their cups with water. John's cup is the orange cup and Mary's the blue one. The robot decides to first fill John's cup, the orange one, and so he does a legible movement towards John, moving sideways away from the blue cup towards the orange one. And from John's perspective, this movement is enough for him to clearly understand the robot's intentions and understand the robot's idea. However, from Mary's perspective, the movement is not so clear and she needs the better part of the movement to clearly understand the robot's intentions. This is because, from her point of view, the robot is not moving in a curved way away from the blue cup, but instead more in a straight line that does not move as far away from the blue cup as intended. So, in multi-part interactions, legible movements must be legible for everyone, and so the legibility metric must incorporate these different perspectives to make the legible movements legible for everyone. However, while combining these different perspectives, we must be careful with three aspects of multi-part interactions. The first one is that by combining the different perspectives, we must not favor one user above the others, otherwise we'll fall back on the previous case where one user has all the understanding and clearly easily understands the robot's intentions, but the other users, on the other hand, do not have such a clear understanding of the robot's intentions. Secondly, with these different perspectives, we can have better information and worse information regarding the robot's intentions. From the example before, we can see that John has a better perspective over the movement than Mary that needs a more complex movement to understand the robot's intended target. And finally, by combining the different perspectives, we must keep the movement inside of all users so they can interact with the robot safely and in a fluid manner. So, we developed Melo, multi-user legibility, a framework that equally averages all the different perspectives over the movement in order to create the legibility metric for the robot. This way, we give the same weight to all the participants interacting with the robot, and so we do not favor one user over the others, not falling back on the problem before. We also avoid promoting bad perspectives because by giving all the users the same weight, lower perspectives, worse perspectives are averaged out and balanced by better ones, and so the movement is legible for everyone. And finally, by equally averaging all the participants, we keep the movement inside of all the users, because as soon as one movement goes outside the view of one user, that user's perspective pulls it back inside of everyone. Regarding the user study, in the user study, we answered the question, in interactions with multiple users simultaneously, does combining their perceived views of a robot's movement improve the movement's legibility? To that end, we postulated two hypotheses. The first one was that humans paired with our move framework generated movements would find those movements clearer than those paired with the traditional single-user approach, or SU. Secondly, we postulated that humans paired with our move-generated movements would understand the robot's intentions quickly and with more confidence than those paired with the SU-generated movements. Our study had the following setup. Each participant would watch 3 sets of videos. Each video would be of a 20-second movement broken down in 3 snippets, one of 6 seconds, other of 12, and the last one of 18 seconds. Between each set, we would randomize the participant's position between the 3 positions of the users in the image before you, and we would randomize the robot's target between the soda can, the telephone, and the Remodeck. Across the 3 sets of videos, participants would either watch only move-generated movements or SU-generated movements. In this video, we can see a movement, a full 20-second movement, of the robot moving towards the soda can, viewed from the perspective of user 1. This video would be broken down into the 3 snippets of 6, 12, and 18 seconds to be presented to the participant. At the end of the study, we recruited 315 participants through mTurk. Their ages were between 23 and 76 years old, with an average of 42 years old. 94% of them were employed, 2% were students, and the rest did not divulge their occupational status. For each participant, we measured the time they would take to correctly predict the robot's target for each set of videos, with either being 6, 12, or 18 seconds for correct answers, and 20 seconds for incorrect answers at the end of the set. We also asked each participant to rate their perceived clearness of the movement on a 10-point Likert scale, as well as their confidence in their predictions, again on a 10-point Likert scale. For the average perceived clearness, Mu was rated higher than Su with a significant difference, thus supporting our first hypothesis that stated that participants paired with Mu would find these movements clearer than those paired with Su. Regarding the average prediction time, this was significantly lower than for participants paired with Mu than for participants paired with Su, with the added aspect that participants paired with Mu were more prone to take the least amount of time necessary to correctly predict the target. Regarding the average prediction confidence, this was again higher for participants paired with Mu, significantly higher, than for those paired with Su. These last 2 results are in line with our second hypothesis that states that humans would understand the robot's meaning quickly and with more confidence when paired with Mu-generated movements than paired with Su-generated ones. So, at the end of this presentation, we know that Mu is a new framework to generate legible movements in multi-party interactions. Mu, indeed, was proven to create movements with which humans have an easier time interacting, better understanding the robot's intentions, with clearer movements and with faster prediction times, and we found a 10% improvement of prediction speed for participants paired with Mu than for those paired with Su. Thank you everyone for being present in my presentation.